Okay, thank you for the introduction and for the invitation to the seminar. Okay, so I was saying that this is joint work with Albert Cohen, who's my PhD supervisor at Laboratoire Jacques Lilians in Paris, and with David Krieg and Mario Ulrich, who are at JKU in Linz. Okay, so let's start with a bit of motivation for the setting. Let's fix some context. I want to solve a parametric PDE. So P here is a partial differential operator acting on U, which will be my solution, and it depends on some parameters. Sorry for the notations here. I denote X as the parameters. So I will take them in a domain D of RD, for instance. Okay, and what I want to solve is my PDE, so finding U depending on the parameters X. So I'm just doing the forward part from parameters to solution. I could be also interested in a quantity of interest F, which depends on the solution. And I will focus on this aspect since I will take a scalar function F with values in R or C. Okay, so what do I want to do with that? I want to approximate F in an accurate way with the least possible number of evaluations of my function. So what does it mean in terms of PDE? I have a numerical solver, which is very accurate. So here I assume it is almost exact. Each computation, so the computation of each function value for fixed parameters takes a lot of time. So I want a small number of exact solves with my numerical solver, which I will denote f of x1, f of xn. And then, starting from that, I want to reconstruct a function f on the whole domain D. What is the point of doing that is that then, if I have to compute the solution for a large number of parameter sets, I will use my approximation of f, which is much faster to compute than the exact solver. Okay, then I know that I have these exact solves, these function values, and I will also assume some prior knowledge on the function f. So remember that f is a function of the parameters. So here, if I talk about smoothness of f, it is with respect to the parameters. To denote that, I will assume that f is in some function class f, a class of smoothness or whatever. Okay, and now what's interesting is that the points xi at which I will compute the solutions, I can choose them. I can choose them wherever I want in the domain D. And the question is, where do I put the sample points in order to get a good approximation of f over the whole domain D, which I will compute in L2 error? Obviously, another question is how much sample points do I have to take? Here, the quantity is n, and I want it as small as possible. Okay, mu is just a measure, a probability measure. Where does it come from? I will measure my error in terms of L2 norm with respect to mu. Okay, so if there is a zone in the parameter domain in which I'm particularly interested in, I will choose a mu that is larger in this section so as to make smaller error in that part. Okay, so that's the setting I can choose. Okay, so let's recap all that. Now D is my domain, and I just have a class of functions f, which is embedded into L2. Okay, L2 with measure mu. My goal is to approximate f based on point evaluations of f at chosen points xi. And to do so, I will study a quantity which is called sampling numbers, which tells me exactly what is the best, worst case error. Here, I take the supremum over all f in the function class of my approximation error in L2 when I approximate f by a linear interpolation based on function values f of xi. Okay, so I don't know what I want to, what bounds I want to prove with that. It depends, of course, on the function class f. And so the assumption I will take on f are implicit. In fact, I will assume that f can be well approximated by a linear operator. So how do I write that? I study the Kolmogorov weights, which are similar to sampling numbers, but instead of having function evaluations at sample points, I can take any functionals. Okay, L1, Lk are linear forms acting on my function f. Okay, and here I'm doing some reconstruction on a linear space generated by phi1 to phi k. So in fact, what happens is that the best approximation of my function class could be just a linear projection onto a vector space of dimension k. Okay, so this Kolmogorov weight is in fact the approximation corresponds to approximation numbers. Okay, so what I will do next is saying, assume I have some decay on the Kolmogorov weights, which is given by the class f I have in my prior. Then what can I say on my sampling numbers? And obviously, well, an algorithm based on sample points is a bit harder to find since point evaluations are linear functionals, obviously. Then Gn is larger than Dn. And I want the opposite bound. How can I bound Gn by Dn from above? Okay, let's say a simple, stupid example showing that I cannot just bound Gn by Dn. Here, if I take f, well, for instance, a space of constant functions plus some L2 error, then point evaluations are not continuous. So my f of xi could be anything, and then the approximation will be anything which has nothing to do with f. Okay, so I need some assumptions on f, or I'm in trouble. There are different ways to solve it. Here, the problem was that I was in L2 and in L infinity, for instance, point evaluations are continuous, so the problem disappears. And that's one option. I will look at Kolmogorov weights with respect to the L infinity norm. That's possible, and it gives some positive results from Limonova and Temlyakov on the sampling numbers in L2. Okay, another option is to say, okay, I cannot bound Gn just by Dn, but I can bound Gn by the tail of all Dn's. In fact, my class f is small only in one direction if I bound just by Dn, but if I bound by try to bound it by all the dk for k larger than n, or here for k larger than m with m close to n, then I will say that my class f is inside a box which is small in all directions. Okay, so this tells me that I cannot have some weird spikes as in the example before, and it will give me some information about sampling numbers. Okay, so that's an assumption I could make, and there's been a lot of work to improving such bonds from Kammerer, Tino Ulrich, Volkmer, Nagel, Schaffer, Mario Ulrich, and David Krieg too. Okay, maybe they started the thing. Okay, so there's been a lot of work, and I'll come back on that later in the talk. A third option, which I want to start with, is adding a randomization in the sampling numbers. We saw in the example, in the previous example, that there was a problem just because the function was spiky exactly at my sampling points. But what if I take random sample points? Then most of the time, the point evaluation will not be on the spikes of the function. And so I will get a reasonable idea of what my function looks like. Okay, so instead of sampling numbers, I will use randomized sampling numbers as I define just later in here. So what do? Instead of picking points x1, xn, which will be fixed, whatever function f could be, I will take a random distribution sigma over d to the n. So it's a random distribution of n sample points. And then I will look at the error for a function f when I take the expectation of the L2 error with respect to this distribution sigma. Okay, so here what it says is that for a given f, with high probability in some sense, I'm doing a good reconstruction. Okay, so I recap from the beginning. Here, if I have a bound on this randomized sampling numbers, it will tell me that for any function f in my class, and probably the one I'm interested in, I will have a random sample from which I have a reconstruction algorithm which performs well. Okay, so yep.
Go ahead.
So you changed the approximating function. Right, so it's not written anymore as a sum of xi times phi xi.
Before it depended just on the values of the xi, because the points are the values of f at the xi. Okay, now the points xi themselves are not fixed since they are random, and so phi can also depend on the position of the xi. Well, in the previous example, in the previous definition of
you still assume that you land in an n-dimensional space.
Yep.
You have to say that. Or maybe not. I don't
Indeed. Okay. So here the difference is that phi were chosen after fixing the points xi. So they depended in some sense on the points xi. In randomized sampling numbers, yep. Well, the point xi are chosen at the end, so phi might depend on it, but it's the same thing. Okay, what's important, as Hilbert mentioned, is that phi goes to a space of dimension n, a linear space of dimension n in N2. Okay, so
Yoshi, you had a question?
Yes, I guess it's related to Fabio's question, but you have f of x1 to f of xn, but do you use that information linearly or not non-linearly? The question.
So here, okay, it's not clear from this definition. I should have put it somewhere. What I'm doing is linear. Okay, so phi is linear with respect to the function values. Okay. And it goes in a space of dimension n independently of the values of the points xi.
Sorry. Have you got a constructive way to choose the optimal sigma? If there is
that's
one?
a very interesting question. I'll come to that later. In fact, we have a constructive algorithm for phi, which is almost optimal. The difficult point here will in fact be how to choose sigma or how to choose the sample points xi. So I'm spoiling a bit. In the end, what we will say is that we have very efficient reconstruction algorithms for linear algorithms, they're almost optimal. But the difficulty is how to choose the sample points, which were the example sets of parameters in the beginning. Okay, so I skip about how things are well defined since it's point evaluations in L2, there could be problems, but with the expectancy, the problems disappear. And now what I have is that the Kolmogorov widths, so the widths with linear functionals, was smaller than the sampling numbers, but the randomized sampling numbers are in between. Okay, why is that? Because okay, I'm still doing some linear algorithms, so I'm larger than the best linear error. And if I take the randomized points to be fixed, in fact, I go back to Gn. Okay, and what I want is to compare Gn randomized with the Kolmogorov with Dn. And we have precisely a theorem saying that up to a constant, both are the same. So with n a bit larger than m, but just up to a constant, we get a comparison between the randomized sampling numbers and the Kolmogorov weights. Yep. F here is the class of functions, and here what's funny, in fact, is that it could be any class of functions in L2. Of course, if you take the full space L2, the M will be infinite. Okay.
So no convexity or balanced or whatever, there's no condition on F. Subset in L2.
It's just a compact set.
Okay, the constants C and K are independent of F, and F, well, the interesting non-trivial case where the Kolmogorov weights are finite are when F is a compact set of L2. Okay, so now how will I choose the points, which I said was the difficult part? Well, in fact, I will start by picking them IID. Okay, that's the simplest thing I can do, and it already works pretty well. IID, okay, but not according to the measure mu. In fact, there is a trick here, which says that if I pick them according to mu, depending on mu and f, I could have something as little efficient as I want. Okay, optimal or quasi-optimal, I need to multiply mu by a density, which will tell me in some way where is the important part of functions from f in the domain D. Okay, so here, if I take an orthonormal system of Vm in L2, so what is Vm here? Okay, I have to tell it here. I had my Kolmogorov weights, which said, okay, there is a best linear algorithm, or almost best, that projects all my functions onto a linear space of dimension m. I fix this space Vm, okay, and I take an orthonormal basis of it. And now, well, the density rho will in fact be independent of the choice of the basis. That's just seen by Cauchy-Schwarz. And it will tell me where I have to sample points. Okay, if my functions phi have a large amplitude at some point, I will have to sample points in that domain, in that subdomain of D. Okay, and now since my sample points are not with respect to mu, I will need to add weights to compensate in some sense for the fact that I subsample more heavily in some parts than in others. So I will put weights that are inversely proportional to rho. And what I will perform as an algorithm, I told you it was very simple. It's just a weighted least square reconstruction. Okay, so here, if I call n my discretization operators, which takes a function and maps it only to its function values, which is the only part of the function that I know, with the weights, then the weighted least squares approximations is just minimizing the discrete L2 norm of f minus my approximation. Okay, so here I can rewrite it as a sum of squares of the f of xi minus g of xi plus weights wi squared on top. Okay, so this is why it's called least squares. And we see that if I remove the n and I took L2 error, I would be optimal. So here, what I'm saying is that this discretizing of the function and taking discrete norm, I want it to be close to the continuous L2 norm, which measures my error. Okay, and now I can rewrite it in matrix form with the Moore-Penrose and inverse of a matrix G. So here, I told you I had an discrete norm, and here G star G is just the gram matrix of the discrete inner product associated to it. Okay, and so if I take the Moore-Penrose inverse of G applied to the discretized F, which is the data I have on F, then I can compute my approximation, well, my coefficients in the basis phi j. Okay, I'll try to be a bit fast on the proof. So what happens is that I have basically two conditions. The first one tells me that I have to be stable in some sense. So G was measuring how close was my discrete inner product to the continuous L2 inner product, okay? And so it tells me if there are enough points, okay? So I need the inverse of G to be well conditioned, otherwise I got instabilities. And the other part is that I want the discrete norm here, the discrete norm of the discretized function, to be close to the continuous norm. Okay, and I apply it not to the function f itself, but to its residual. So the residual is f bar. I take f and I remove its projection onto Vm, which is the optimal approximation. So when I look at the remainder, it has to be controlled in one norm by the other norm. And then the proof goes as follows. I just apply Pythagoras to separate, well, the part that is already almost optimal and the error I'm making by using least squares instead of linear, well, the optimal projection. And then when I look at this, the second term in expectation, I can rewrite it thanks to the matrix forms in terms of the inverse of G and the discretized L2 norm. And I use both my conditions to say that the first one is bounded here, the second one is bounded here. And what I get is in the end is that my L2 error for function f is bounded in expectation by a constant times the Kolmogorov width. Okay. And now what I'm saying is that this argument works for all functions f from class large f, which proves my bound. Yep.
The big F that you.
Okay.
There was again a bit louder.
Sorry. I was asking a question about the class F, big F. And
there was no definition of the class F. It's, I said it's just a compact of L2.
Okay, can be.
Okay. So for the moment, it can be any function. And what I'm saying here is that if I can approximate the functions from large capital F by linear operations, I can reconstruct them by point evaluations. Okay, I still need these two conditions. So here comes the choice of the weights and the measure. So for the second condition, we start with that one. Well, if I take the expectation of the discrete norm, I fall back on the continuous norm, which is perfect, exactly what I want with the constant one. It's cool. Now for the Graham matrix, what I need is, yes, the smallest eigenvalue of the Graham matrix to be bounded below. And that I will use, for that I will use a concentration inequality. I see that when I take more and more points, well, by some kind of ergodicity, I will converge to the expectation of this, which is the identity. Okay, so as the number of points gets large, I concentrate to the identity and I'm well conditioned. Now, I want to take a small or fixed number of points. So I will use a concentration inequality to tell me that I only need, in fact, n of the order m log m. Okay, so n of order m was the optimum, and here I will need a bit more for this exponential concentration inequality. And here, well, I used one concentration inequality for matrices, but others could work. A matrix Chernoff bond works well. Anyway, what happens is that here, with my budget of sample points of m log m, so I had to do m log m numerical solves, then I have an accurate reconstruction of f in expectation. I'm not exactly satisfied about this m log m, so I want to improve it a little bit, and to do so, I will try to reduce the number of points. Oh, okay, I forgot something. Here, this works only with high probability. Okay, because here it's probability larger than t and then exponential in t. So I can take t close to 0, but not exactly 0. So what I will do for avoiding this is saying each time my sample doesn't work, I resample it until I get a sample that works. I can test this, and since it happens with high probability each time in a small number of steps here, in expectancy, it takes 2 steps if I take the t equal 1/2. So I will get a good sample. Okay, so now it's not in high probability, it's I'm sure that my sample is good for approximation in expectation. And I still have this budget m log m. And what I want to do is reduce this to a budget m. Remember that the budget here, so n, is the number of numerical solves I have to do. So if each numerical solve takes a lot of time, I really want to have the least possible number. Okay, and here is a theorem from linear algebra saying that if I have a sum of rank 1 matrices summing to the identity, then I can split it in 2, and both parts are close to identity over 2. Okay, so here, well, I just got an upper bound telling it's smaller than identity over 2 plus some error, but I can have the lower bound by looking at the second part. And my assumption was that this sum was exactly the identity. If I multiply by some matrices on the condition above, so on the yi, I can relax this hypothesis. Okay, so this tells me I can divide the sample size by 2 and just make a small error in this condition. Okay, so I will apply it here, but just before that, I'm gonna reiterate this thing, because what I want to do is not just divide the sample size by 2, I want to divide it by log m, okay, or by a larger number. Okay, so I will do it iteratively, each time dividing by 2. And here I got a more general result telling me that I can divide my sample points x1 to xn into t sets, such that each one is well, close to the identity up to constants. And well, the constants are a bit ugly, but that's not a problem. Now, what if I apply it? Okay, I will keep one of these partition classes and say my subsample is just the elements from this partition class. So the xi with I in the JS that I chose. Okay, and what will happen at the end is that this sum will be bounded by the identity. And here, the yi are just were just the lines of G. So I had G star G, which was close to the identity in the beginning. And what I say is that it remains close to the identity after subsampling. Okay, and having it close to the identity means the smallest eigenvalue is small, which is my stability condition. With this, okay, I preserved the second condition. The first condition, do I still have the second one? Well, yes, because I chose the partition class at random. So in fact, the probability that a single point is chosen is not affected by the subsampling. Oh. And with this, I got my two conditions, and this proves the first theorem. Okay, so now, let me recall that the first theorem was bounding randomized sampling numbers with a bound in expected L2 error. And here, I might not be happy with that. For instance, this result is not uniform. It means that for every function, my sample chosen at random will be good in expectation. So for a given f, the sample x1 to xn might be good. And then for another function g, the same sample might be bad if I fix it. Okay, so now I want something more uniform. So I would like something in terms of sampling numbers, the deterministic ones. And to do so, I will work in the setting of reproducing kernel Hilbert spaces. I see I'm a bit late, so I will skip the last part. Okay, so just a brief reminder, a reproducing kernel Hilbert space is a Hilbert space with a kernel K, which can be written as a sum of singular values times basis functions. So phi here is an orthonormal basis of L2, and the dk times phi k are orthonormal elements of the Hilbert space H. Okay, and here I will consider a specific function class f, which is the unit ball of this Hilbert space. Okay, so that's a specific situation in which I have a lot more assumptions. In particular, I assume that my kernel K has finite trace, which is the assumption above. And what does it tell me? It tells me that the singular values, which are in fact the Kolmogorov weights, that's why I denote them dk again for this class f. Well, these dk are L2 summable, okay? And that will lead me to some results as the one I presented in the beginning, in which I bound the sampling numbers by the L2 tails of the Kolmogorov weights. I'm saying if the decay, the Kolmogorov weights are decaying fast enough, then the GN are 2, the sampling numbers are. Okay, and there has been some improvements first to remove some logarithmic factors, which reminds you of what happens just before. And well, first, there were 2 logs in the beginning. One was removed by Nagelschaffer and Ulrich, and what I'm going to tell you is that we removed the second one. Just to tell you that if we remove the second log, we're optimal since there are examples where the lower bound holds. So we cannot have GN comparable to DN in general, but with that tail, we can have a sharp bound. Okay, and that's precisely what we say here, that we can remove the second log and bound the GN by the L2 tail of the Kolmogorov weights. Okay, and here is an example. If I'm decaying like n to the minus alpha, then for alpha larger than 1/2, remember that I need the Kolmogorov weights to be L2 summable, then the sampling numbers decay by at the same rate. But in a critical case, they decay a bit slower, okay? And this is sharp again because of the lower bound just before. Okay, I will skip most of the proof just to tell you that the sampling density here looks like the previous one. There is still the Christoffel function, but there is a second part for the reminders, okay? So for the elements phi k with k larger than n. So the basis functions that are not in the approximation space of Vm. Okay, with this, I'm doing pretty much the same thing. So I'm defining yi, a gram matrix J, an equivalent for the remainders. And I'm using some concentration, so I still have two conditions. The proof is the same, and I can use the same concentration inequality. Okay, and with that, I got the first estimate, which told me I have logarithmic factors, and I'm almost good. Now, how to remove these log factors? Well, in fact, I could have removed any factor I wanted. Why is that? Because here, if I got a sum of rank-run matrices that looks like the identity above and anything between 0 and the identity below. So here, what's important is that it could be infinite matrices. Then I can subsample my sum in order to preserve these bounds by identity above and something between 0 and identity below. Okay, so for infinite matrices, I could not be close to the identity just by rank arguments, since the sum here is of rank n. So it's normal that I cannot get the full identity here, but I can get almost it, okay? So here, what's important is that the first block corresponds to the space VM in which I will perform my approximation. And the rest here, which might be infinite dimensional, is the orthogonal, which will create some kinds of instabilities. Okay, and here what I'm saying is that I will be stable and control these instabilities. I skip the proofs. There is a change of basis to reduce to finite dimension. And okay, because what I wanted to apply was the result above saying in finite dimension, if I'm close to the identity, I can subsample. Here, I'm not in finite dimension, but my sum is of finite rank. So by a change of variable, I make it of finite dimension. And then how to make it close to the identity? I was below the identity. I had the identity and something smaller than the identity. So I will add artificially some vectors, which I can remove later, so as to get close to the identity. So here, well, I had a sum until n. I add vectors between n and q. I get closer to the identity. I then apply the same tool as before, the same corollary, to get, well, which is the iterated version of the main algebra theorem. And this gives me partition classes J1 to GT. And I keep the one which has the fewest true sample points. Okay, I added artificial sample points which did not have a meaning, but I want the smallest number of true sample points, which is the one that will appear in the end. Okay, do I have? Okay, okay, I'll try to be fast. Just another point to say that, well, this was, the first one was with L2 summability in reproducing kernel Hilbert spaces. And the RKHS setting might be a little too constrained. So I want to know what happens for general classes of functions. And what happens is that I have the same bound, but in LP, in little LP, instead of L2 for P smaller than 2, which is a bit weaker. Okay, the proof can be deduced from the previous one just by creating here, where is it? Here, I will create reproducing kernel Hilbert space that contains my class F. And then I will apply my result on reproducing kernel Hilbert spaces. Okay, well, a bit of technicalities. So here, this is what I can deduce, and it gives me some important intuition. So I'm still taking the examples where the Kolmogorov widths, so the widths of my class F, decrease with some polynomial and logarithmic rate. And what I have is that I get a sharp bound again, I can find examples where these rates are matched. And what happens is that when alpha is larger than one half, so if the width of my function class decrease fast enough, I recover the exact rate. But here, in the critical case, I knew that I couldn't have Gn close to Dn. And in the RKHS setting, I had Gn of order Dn times square root of log n. And here I got another factor, square root of log n, which appears. Okay, so that's just to tell I have some log n factors that cannot be removed. Yep.
This accolade, maybe you didn't mean Gn less than Dn, but less than n to the minus alpha log minus beta times n.
Okay, up to a constant is the same.
Well,
Yeah, okay.
unless Dn is exactly equivalent to
Indeed. Here I'm assuming Dn is equivalent to that, so has exactly this rate. Okay. So that's all. The proof is again similar. So a concentration inequality, and then a bit of manipulations between LP and L2 norms, which explains why I cannot have the result exactly in L2. I'll skip that, and I just had a few final remarks on complexity, on algorithmic complexity, because what I presented were very simple algorithms, weighted least squares, and we could do other stuff that is polynomial in complexity, easy to implement. But the difficult part comes from choosing the points. And here, I first use a density, which is based on an infinite sum, which is hard to compute. So I probably need some truncation or bounds on this density row. And then the sample reduction has an exponential complexity. The theorem from Marcus Spielmann-Srivastava that we used to reduce the sample was totally unfeasible. But there is a similar result, a bit weaker, which has polynomial complexity and which we're trying to adapt to this context. So that's all, since I'm in a hurry. Thank you for your attention.